Good morning, everyone. I will just start. Today I will tell you about druggability method, a simulation-based method to study druggability of target protein. And I will demonstrate how to use a VMD plugin to set up simulations and analyze simulations. Again, I will make a quick survey. Who does drug discovery related research here? Okay. Do you use simulations for drug discovery purposes? Not yet? Okay. So target druggability, what is it? Given a biological target, druggability means the ability to bind a drug with high affinity to this target. Okay. So if I show you two drug targets here, would you be able to tell whether they are druggable or not? Now on the left-hand side, you see you see surface representation for these targets, and you see that coloring is based on electrostatics. And looking at surface properties and cavities on the protein, you may be able to tell for some proteins, but probably not all, and we will see why. Now this question is an important question in drug discovery. People spend 15 years to discover a drug and billions of money. You can find a protein that is involved in a disease, and you can spend billions, but after a decade of research, you may realize that it's not druggable. Everything that you spent on a target was worthless. And I have seen that this has happened in a drug discovery in a pharmaceutical company. What do we know about the druggability of the genome? We know that there are 30,000 or less genes in the human genome, and it is predicted that only 3,000 of these genes are druggable. And it's also predicted that there are about 3,000 genes that are involved in human diseases and that they modify diseases. And only a subset of these disease-modifying genes and druggable genes are drug targets. So, if you want to pick a target, you would like it to be here. And this analysis is based on precedence-based analysis of drug targets. So we know that all kinases are druggable. They fall in these categories. And we know that GPCRs are druggable too. They fall in these categories. And we know that PTPs are not druggable, and they fall in this category. So, yeah.
What is something that is not druggable?
Something that is not druggable.
Yeah, like a GPCR that is not druggable. Means there is no drug developed for it yet, or?
It means that people spent 10 years and couldn't find a drug that hits it. So they started to think that it's not druggable. I mean, but the general thinking is that all GPCRs are druggable, but most of them may not be involved in a disease. Finding a drug for them is useless. PTPs, protein tyrosine phosphatases, for example, I will show one of them. People spent decades and couldn't find anything. And after a decade of research, they started to think that they are not druggable. So this analysis comes from the knowledge, the experience that people have on these targets. But you might find a protein that is not studied before, a new protein family. You crystallize a new structure. Would you be able to tell whether it's druggable or not? Now, I will tell about computational methods and particularly a simulation method to be able to predict that. And I want to discuss a little bit about why drugs bind proteins. Now, for each drug, you might have seen they calculate a log D value. This is the partition coefficient. This value tells how much this drug molecule, this is a drug molecule, it was FDA approved in 2011. This log D partition coefficient tells you how much this drug molecule likes to be in membrane or in octanol. Okay, so you see, again, the coloring is based on electrostatics. This part of the molecule would like to be in water, but most of this hydrophobic surface would like to be in hydrophobic environment. And the partition coefficient tells that if the volumes of these two environments were the same, you would find 100 copies of this molecule and 1 copies of this molecule in water. And since they don't like water that much, they like to bind proteins, but they would like to find a cavity that they would fit in, and a cavity that's probably hydrophobic, right? That's the cavity where this compound goes. Okay, so this is a close-up view of the cavity. You see the inside of the cavity is hydrophobic, and the hydrophobic part of the compound matches there. The water in that cavity is replaced. You know, water is not probably happy in this cavity. It doesn't form. It's very restrained. It cannot form hydrogen bonds, and anything that fits shape-wise in this pocket would remove the water from there. And this part of the molecule, you know, it's positively charged, and people in pharmaceutical companies, to increase the solubility of drug molecules, they usually attach a charged part to the molecule. It doesn't contribute to binding of the molecule, but it just contributes to solubility of the compound, so that it will be more available in the cytosolic environment to bind the protein. Now, people have done experiments to assess the drugability of target proteins. You can imagine that one can do X-ray crystallography. You can try to crystallize your protein in presence of small molecules or fragments, and wherever these fragments bind in the X-ray crystallographic structure, that could point to a druggable site. Or you could do NMR screening, and in this paper they screened target proteins in presence of a variety of fragments. So they had a set of 1,000 fragments, and they screened the protein like 50 times. Each time there were 20 different fragments in the test tube, and wherever the more fragments bind was corresponded to sites that are known to be druggable. And then there are docking methods to assess the druggability, right? Here, this is pretty much, you know, you are trying to reproduce these using docking. You have a static structure of the protein, and you dock a bunch of solvents and probes, and you see where they dock favorably. And then you do a clustering analysis, and wherever you see enrichment of probes and a variety of probes, it points to a druggable site. Now, sometimes you don't even need to do docking, you know. The highest contribution to binding of a drug comes from the hydrophobic effect. You need to have a concave pocket, and you need to have a hydrophobic surface. If you calculate the concavity of the pocket and the hydrophobic surface area, you can relate it to druggability of the target. Here, druggability or druggability index is measured by affinity of the drug, okay, the maximal affinity that a drug molecule can achieve. So if you estimate that the druggability of a target of a site is nanomolar, it's very good. Here, let's see, it's been a while I didn't look at this graph. It shows the relation oh yeah, so it's in this model they used a fraction of hydrophobic surface area and the curvature of the pocket, and the combination of these two. So the fraction of hydrophobic surface area is higher for druggable targets. For difficult targets or for non-druggable targets, the fraction of hydrophobic surface area is much less. The concavity of curvature of the pocket is similar for druggable targets. It's a deep pocket like this, I guess. And it's widespread for difficult targets, and you know, a combination of two is able to predict the druggability of targets nicely. And this is just an example. I won't go into details. And here is their predictions. You know, you see a bunch of targets here that are druggable, and this is calculated druggability in terms of nanomolar maximal achievable affinity. Okay. And you might know many of these targets. You see kinases here. You see HIV, RT, EGFR. I don't see any GPCRs. Maybe due to lack of structures. You need a structure to be able to calculate this. And you see some hard to drug targets. One of them is protein tyrosine phosphatase 1B, and the other is catepsin. Now, these two methods, docking methods and structure-based surface area calculation methods depend on a static structure of the protein. Okay? Proteins are flexible. They may change their shape when they bind a drug, right? And if you have an unbound structure which would change its shape, you might calculate that predict that it's not druggable. Here, an example, they used MD snapshot evaluation method. They started with, so this structure is an unbound structure. The green thing is overlaid onto that structure. When you calculate the druggability of this structure, you see there is some overlap with the bound protein here. This is predicted to be non-druggable. But when they simulated, they made a very short simulation in the order of nanoseconds of this protein. And in the protein changed its shape. They collected frames from this simulation and recalculated druggability. And some of the frames from that short simulation was predicted to be druggable. In fact, this target is known to be druggable. So it shows that, you know, for targets, if you don't know they change their shape or not, it may be better to use a simulation-based method to estimate their druggability. Now, what I will talk about is mostly about probe simulations, right? You know, people took a static structure of the protein and they docked probe molecules to that protein to see where they go. But you can do that in simulations too, right? You need to prepare a system and you need to remove some of the water molecules and replace them with probe molecules. And what you will do is just simulate the system for a while and see where those probe molecules go. Now, in these simulations, the probe molecules are small. You know, you could very well simulate a drug molecule in a simulation, but if you have limited resources, like if you can simulate 30, 40 nanoseconds, you know, simulating a drug molecule, you wouldn't see any binding. That big drug molecule would need more time to rotate and adjust itself and find its binding site, right? But by using small probe molecules, you they diffuse fast, and several tens of nanoseconds is plenty of time for them to bind, locate binding sites and bind them. And you know, if you use a specific drug molecule, you would expect it to make very specific interactions. Since these are small molecules, they will make specific interactions, but they are small. And if you imagine a drug binding site, you know, a few of them can get together and, you know, mimic a particular drug. So this set of molecules can be widely applicable to different proteins. They are not, you know, individually they make specific interactions, but if you think of a drug-sized molecule, they can get together and assume different orientations or different groups, clusters, and they can sample different sites effectively. So, you know, what are these probe molecules? We investigated FDA-approved drugs, and we calculated how many times we observe a moiety in a drug molecule that looks like isobutane or isopropanol, isopropylamine or acetic acid. And, you know, in 70% of approved drugs, we observed isobutane fragment. In 57%, we observed isopropanol, and in at least 20%, we observed these four solvent or probe molecules. And you see, you know, when I think of a drug, I usually imagine a neutral molecule. I don't think of a charged molecule. But this study shows that 35% all the available drugs are, only 35% are neutral. The rest are charged, positively or negatively charged, or they are Zwitter ionic. So this addition of charge is just to increase the solubility of the drug, not necessarily to make it increase its affinity. Then, you know, based on this analysis, we decided to use this set of this composition to mimic a drug molecule. In this composition, you know, it doesn't matter how many probe molecules we put in the system, but always 70% of probe molecules were isopropanols. So these isopropanols mostly mimics the hydrophobic part of the drug molecule. And then we had 10% isopropylamine and acetate to mimic charge interactions, and acetamide to mimic polar interactions. We didn't include isobutane in simulations because isobutane is completely hydrophobic and it likes to aggregate. You know, in a simulation with with isobutane, you would see isobutanes forming islands away from the protein, which was not really useful to see what we wanted to get out of that simulation. Now, we use these probes and we take a target protein, we place it in a box of probe molecules, and the probe molecules are pretty much randomly distributed, not in this figure, but in general. See, they are randomly distributed. The space around the protein and between the probes is filled with water. So we have water and probe molecules. And what we want to see is where probe molecules go, where they bind favorably and more favorably than water would bind, right? So in this box, in this simulation box, we have 252 isopropanols, 32 of these, and 7,200 water molecules. Now I will show you this simulation and you'll see how it works. Okay, this is a drug target. It's targeted in anti-cancer research, as far as I remember. Now this is an allosteric binding site of this target. You see the drug molecule, an inhibitor. The inhibitor was not there in the simulations. It's just there to show you where the binding site is. And in the beginning of the simulation, the protein does not interact with any probe molecules. You see two probe molecules that are close by the protein. When the simulation proceeds, you will see that the probe molecules that interact with the protein will become visible. And I want you to pay attention to these specific interactions of the inhibitor. It has an oxygen here. It probably does some hydrogen bonding. And it has a positively charged amine group here. It's positively charged. And you will see that probe molecules, probe atoms of the same type is going to find, yes, see more and more probes are interacting with the protein. They are coming to the binding site. The binding site is changing its shape. You see an oxygen of the probe is mimicking oxygen interactions, and nitrogen is coming close by. So, you know, the nice thing about simulations is protein is adjusting itself. If you do docking or if you do a structure-based analysis, this won't happen. You see the drug binding site is completely filled with probe molecules. This is only a 40 nanosecond simulation. And we tried that, we saw that it's reproducible. You can, of course, simulate longer and see more of this site. What will happen to it? It will stay in that conformation longer, depending on your target. Now, from this simulation, 40 nanosecond, we save 10,000 frames. And now it's time to analyze those frames and find out which sites were enriched with drugs, right? Now, this is the initial state, and this is the binding site. Some of the probes are not shown so that the binding site is visible. And we save 10,000 snapshots. So we make a grid-based analysis. We align these snapshots based on the initial structure of the protein, and then we build a grid around around the protein structure. And what we do is simple accounting. So in each of these grid elements, we count how many times we observe a probe molecule. And we count the probe molecules by only considering its central atom. So if you remember, all of these probes has 4 atoms, and there is a central carbon atom. We just count that central carbon atom in each grid element. Just sum up the binding affinities of selected probe molecules. And we assume that, okay, that's an ad hoc assumption or an bold approximation, but we say that the sum of binding free energies of these probe molecules in a given binding site is an indicator of the achievable, maximal achievable affinity for a drug-like molecule. Okay? For this site, the sum of free energies is 13 kcal per mole, and it corresponds to a 0.3 nanomolar affinity. Okay? And I will show you results for a set of test cases. So this was the protein surface that I showed you in the beginning. Is it druggable or not? And looking at this structure, can you tell where a drug-like molecule would bind? Right? Sometimes it is hard to tell, and I wouldn't be able to tell looking at this structure. But we know from structures, PDB structures, that this is the allosteric binding site. Although it looks like charged here, maybe the orientation doesn't help that much to say whether it's druggable. This is the druggable site, and this is the drug that binds here. And the best known affinity for a drug is 0.2 nanomolar for this site, and the simulation that we used predicted it to be, the method I showed you predicted it to be 0.3 nanomolar. It's a close prediction. And you see that site here, in the protein here in more detail, and the allosteric site here in more detail. Now in this figure, some of these spheres are pro-binding sites, and some of them are made larger. If you see a group of spheres that are larger, it corresponds to a druggable site, a prediction for a site that indicating that it's druggable. So here the simulation method predicts the
let's say, take this larger one that you're interested in, put it next to it and see if it finds or what the individual finding is? Smaller one just identify the
Yes,
right?
yes, you can do. You can, doing the experiments may be easier first to see if it binds, and then you can use simulation free energy perturbation calculations to calculate its affinity. Okay, now I will show you how to use the plugin. The plugin became available 2 days ago, and there is a link from the workshop webpage to the. Maybe I can open and show you. So I'll make it part of VMD. I will ask John Stone to add it to VMD, but until he does that, it may take months. You can go to this website, and there is installation instructions. You can download it, and you can find out how to use it. So there is a link to this from here, tutorials, draggable tutorial. You can click this and get that. Okay. Now first I will set up a system. And you might find this plugin useful for setting up simple simulations too. You can add probe. Okay, I'll show you now how. Okay, when you follow the installation instructions, it will be in modeling menu. Will be agree. Now this is the panel for preparing a system, and there are 5 different panels for different tasks, different stages of the process. Okay. Now you need to give a PSF and PDB file. Okay. PSF, and you need to prepare this PSF and PDB files for your system. This plugin won't do that for you. And the PSF and PDB files for your system should include all the atoms that are necessary for function. So if your protein is a metalloprotein, you should include the metal in your system files. Okay. Now this is the protein that we are going to prepare for simulations. Now here you have 4 different options. Okay. You change the percentage of acetate and isopropylamine together. So they have opposite charges and they balance each other. So it's better to put them in the same amount. So you can add more of something, but you need to make sure that these percentages add up to 100%. And then there are 2 more options, okay, for solvation and counter ion addition. It will calculate the charge on the protein on the system that you provide, and it will add necessary counter ions to the system. And you can specify the padding for the simulation box. 6 may be sufficient for most cases, and it will be usually slightly greater than 6 because to make sure that the probe and water ratio is preserved, it may go beyond 6 angstroms. And you will select an output folder, okay, and a prefix. And it will prepare simulation files for you. So in general, I do 2 simulations of 40 nanoseconds in the beginning. And I will specify here 2. And I see if the observations are repeated in these 2 simulations. And if I like one of them, I can extend it more. And if your system has a novel residue or a novel metal atom, and you need to add more parameters to your simulation, you can add those files here. You will specify the parameter files, and they will be included. Okay, I'll fix this. And I'll just say prepare the system. Okay.
So this plugin will completely solve the protein for you?
Yes. Okay. It will add everything that you need for these simulations. So you see the system is ready. You see probe molecules. Some of the probe molecules are out of the box. What it did was it prepared the water and probe molecule, it placed the water and probe box around the protein, but to preserve the ratio of one probe to any water molecules, it removed some of the water molecules, and some of them are out of the box. When you start the simulations, they will be wrapped around the box, and this one, for example, will enter the box from the other side. So this is okay. And you have the counter ions here, large spheres. Now it will show you a log file. In the log file, we can see how many waters and how many probes the system contains, and what is the mass of the system, what is the density of the system, and it will tell you that NAMD files are prepared for you and where you can find them. If I go to this folder, so you see I have a folder for minimization, I have a folder for first simulation and second simulation. There are 3 equilibration steps and a simulation step. This is the productive simulation. And there is a file in case the simulation crashes and you need to restart it. And these 2 simulations will use a single minimization step. The minimization will be used for both of them. And here in this folder you will find the parameters that are used for the simulation. Okay. There is a command file here, a sh file. Okay. All you need to do is just run this file. You need to specify the path to NAMD, and when you execute this file, it will run the minimization, and it will run the first simulation, and it will run the second simulation. Of course, this configuration of this file may change depending on the machine that you are using for simulations. Okay, now using this plugin, let's say you want to do a simple simulation, you want to equilibrate a structure, just that. You can set everything to 0 and can prepare a simpler system. You will have just water and ions around the protein. One more reason for you to use this plugin. So we have fewer log output here. Say system is neutralized, 5 chloride ions are added.
Sorry. So you don't like adding additional ions?
I do.
Yeah, I mean more than just neutralized.
I don't in general. If I were to simulate a membrane protein, then I would. But for a small system, no, I make the system neutral. I mean, I put as few ions as possible. Okay, now preparation of system is done. Then there is this step for calculating the grids. Okay. I have example files in here. Now I have a set of simulations run with the prefix defaults. Defaults is just I used the default probe setting. I select the. Okay, this is the simulation that I. So this is the system that I simulated previously, and I provided these files for you to analyze if you like. Okay. Now, in the analysis step, in the probe grid calculation step, first you select the PSF and PDB files of the system, and then you select a simulation file. Simulation file is just this file. If your simulation crashed and you have multiple DCDs, you need to select all of them. But I don't recommend selecting these equilibration DCD files. Okay, and then here is the selection for making the alignment. All the beads that you show here, alpha carbons, will be used for structural alignment. And I use only the structured atoms for the alignment, so I have a more robust alignment. If I had included floppy parts of the protein, the binding site would not be aligned properly, and the affinities that I calculate for probes could be weaker than they should. Okay. And here are some options to, oops, oh no, I shouldn't have pressed that. This will take a while. Okay, I wasn't planning to show it. I'll just close this. And So in this step, this panel calculates grids. Also, optionally, it evaluates those grids and makes druggability, performs druggability assessment. Okay, if you have not selected this after you calculated the grids, you can go to the next step, assess druggability. In this case, you will select grid files. Grid files have DX extension. Okay, you will select all the grid files for different types of probes. And then these are the optional parameters, but you can change those parameters. For example, this parameter shows the number of probe molecules to merge. Okay, if you are interested for a binding site for a larger ligand, you can make this number larger. Or if you are interested for a smaller ligand, you can make it smaller. And this is the lowest affinity that will be displayed to you. Affinities that are lower than 10 micromolar is considered hard to drug. So I won't show them. I'll just run this. The parameters are explained in the paper, not very much in the documentation, but if you have questions, you can email me and I can update the tutorial with those questions. And I need to select a Python executable. Now, everything that I want to do, I cannot do with VMD, unfortunately. I need to use Python and NumPy sometimes. In this case, the grid files are prepared using VMD, and then those grid files are evaluated using a Python package, Python module that comes with the plugin. Right. In the background now, the analysis is going on, and it has finished. Analyzing grids is usually fast. Now you see the hot spots here. Okay. The hottest spot is here. It is a very small pocket. Okay. Probably what happened is a single probe molecule went into this pocket and stayed there during the entire simulation. That's what I remember. But in this case, we have also similarly hot spots, but it wasn't a single probe. Multiple probes were there. Okay. After this is done, you see again a log file from the Python analysis of grid files. It shows you the hotspots. The first hotspot is completely contributed by isopropanol, and it has this much binding free energy. And you see a list of, I don't know, 51 hotspots. And in VMD, you will see different molecules loaded. I'll make this smaller. The first one, protein heavy atoms, it shows non-hydrogen atoms of the protein. And the second one will show you the probe binding hotspots. And then you will see solutions for different sites. So each site is a cluster of probes, and we identified a solution, a group of probes in this site that has a druggability index that is better than 10 micromolar. Okay. So you see the selected probes here. You can show all of them, or you can show just these. Now, how would you know the affinity of a particular probe molecule? Okay. So if you press 1 and label this probe molecule, it says iPro2. Let's see which one is it. The index of this one is 1, and the residue index is 1. Since indices start with 0 in VMD, this would correspond to the second probe molecule here. So it's completely contributed by isopropanol, and its affinity is negative 2.36 kcal per mole. Okay. Excuse me. One more thing that you can do is, this is just a static picture. We don't know how probe molecules interacted with, how they spend their time in this spot, with what they interacted and how they interacted. For that, you can go to Visualize Results menu, and then you can select System PSF file, and you can select Aligned DCD file. So after grid calculation, there was an option to save aligned DCD file. You can save it, and you can load it for visualization. Delete existing molecules, visualize results. And we will see how probes were. Okay, loading a DCD takes some time. Okay, it's done. Now I have 100 frames loaded here. I can turn on that. I can turn this off, turn this off. And I will also turn hotspots on. Now if I... So this shows how probe molecules come and go into the binding site. And we can look at that highest affinity spot. Where is it? There is still exchange of probes here. They spend longer time, I guess.
Where's the high affinity spot?
This one. This one. I'm doing some averaging. I will stop that averaging, okay, so that probes will look right. So what you can do is go here, representations, licorice. You can color probe molecules by residue ID, or well, residue ID is good, so that we will know whether it's the same probe or not. So one probe spends half of its time there, and then another one comes. It's contributed by two probes. But if we go to another site, so this is how you can find out, why you observed a high affinity site in there. Here, pink comes, gray on 4, 5. It is contributed by many different probes. So this is how you can set up a simulation for drugability calculations, and how you can analyze that. Okay.
So I guess, can you change settings so that, let's say you have an extracellular target and you don't care if it's charged, and you want to look at things that could be a ligand instead of a...
Oh yes, of course. I mean, that's now this supports only 4 types of probes. Okay. Only these probes. You can put as many charged as you want, and you would need to decrease the amount of others. But you can also customize this too. Now there is this charm general force field. Have you heard of that? In the charm general force field, they have parameterized more than 100 small organic molecules, and they have 5, 6 atoms. You have lots of heterorings. You have lots of phosphates, sulfones. Okay, you can incorporate them into your simulation, and this let's see. And this can be your starting position. PSF generator has a function called mutate. You can take a particular probe from here and mutate to imidazole, for example. When I prepared my system for cytochrome C simulations, that's what I did. I prepared a system composed of isopropanols, and I took out isopropanols and mutated them to imidazoles. So you can customize it, and this can be a starting point. It won't do prepare a completely different system for you, but maybe useful for other purposes too. And if you have specific questions regarding how you can mutate and things like that, I can send you short scripts, or maybe I can add them to the documentation. Okay, this ends my talk. Ended earlier than scheduled, so you may have more time to play around with this GUI. Okay, shall we take a break? 10 minutes before